Okay, well, this is our last week. We have 2 class meetings, and we have then we have our final next Thursday. We have the pleasure of actually getting to chapter 9, which doesn't happen all the time. So that take-home test really helped us be able to get to this material. I think what you're going to find with this material is that it's kind of like we're downshifting now. You know, we're kind of like, we're just going to coast to the finish line here. I think this material is a little easier to grasp, but you'll be the judge, all right? Okay, but it's really important information, especially if you're going to take Cal 3. This kind of leads into it pretty good, all right? Some of the things that we do in here. Yes? This will be on the exam.
Everything will be
But I think that the problems when you see what the things you're going to be asked, you'll actually kind of appreciate that. Like I said, it's going to be kind of a downshift.
Is it still take home or no?
Oh, and as far as the take home, I'm opting against that. So we're just going to do the in-class final on Thursday.
And it's going to be comprehensive, start to finish.
I'm going to give you something on Thursday. I have a handout that I'm going to give you that's going to give you a list of what topics you need to look over.
Fair enough.
Okay?
So I thought, good Lord.
But it's going to be mostly focused on chapter 8. Almost 100% chapter 8, and of course some of this chapter 9. Let's get started. Let's see how far we can get. You ready?
Yeah.
Okay, please ask me questions if any of this doesn't make sense, because you really have to understand what's going on here, all right, in order to appreciate what's happening.
Real quick, if you're going to do the video for those problems, could you let us know when? Because I know sometimes students sit in on that while you're doing
The videos for what problems?
the homework solutions.
The ones where you multiply and divide power series?
These and the
Yeah,
eight
yeah.
or whatever. Could you let us know maybe?
I will.
That way, if we can see
Yeah.
it, we can.
Yep.
That'd be awesome. Thank you.
Okay. All right. You mean when I'm going to do them, like so you can be there for them?
If that's possible.
I don't know if I'll have that much of a heads up. I might be
no
like,
worries,
you know, hey, I'm about to go in there in 30 minutes and do the video. I mean, I haven't planned it.
No worries. No
Yeah,
worries.
I'll try, though.
If possible.
Okay.
It's very spontaneous for him.
Okay. Our traditional function, y equals f of x. All right. Going back to college algebra, when we write down y equals f of x, we say that y depends on x. So y is what we call the dependent variable. X is called the independent variable. X is the input, right? Y is the output. And the graph of a function is the collection of all ordered pairs of the form. Normally we write xy, but here I'm writing x f of x to stress the fact that the y coordinate depends on the x coordinate. You give me the x, I give you the y, right? And when we graph these things, like here's the parabola y equals x squared, then as we vary our x, right, the y coordinate changes. So notice that the x, the input, right, actually visually appears on our graph. So the input here, if I put in 4, right, I'm not going to be able to get to 4, but if I put in 4, it's going to spit out 16, right? And nothing new, everything's pretty straightforward.
Never seen this before.
Yeah? Okay. All right. Now, this is some new notation that I just want you to try and understand. When we say our traditional function y equals f of x, I can say the function f, all right, takes in a real number, spits out a real number, so it goes from R into R, from one-dimensional space into one-dimensional space. And then when I graph that, I have one dimension right here, which is our input axis, and another dimension, our output axis, like this. And so we can put them together. So also notice that the x-coordinate, the input is actually the x-coordinate of our point. The graph passes the vertical line test. That's what makes it a function, right? Passes the vertical line test. And that means for each input, right, to be a function, every time you plug an input in, there is exactly one output, right? If that doesn't happen, it's not a function. So let's see some of the problems that we may run into with a traditional function y equals f of x. Can we graph a circle using a single function? No, because when we try it, This is a little bigger than I thought it was going to be. When we try and graph a circle, as I move around this circle, notice that if I try and plug in an x, right? If I try and take an x coordinate, there's going to be two corresponding y coordinates. So like if our x coordinate is 0.656, there's a positive answer and a negative answer. That's what you would need in order to graph this, right? It fails a vertical line test. A single input goes to two outputs. Understand that? This input's the same, but it goes to two different places. That fails to be a function. So we cannot draw a circle with a single function. How do we get around this? How have we gotten around this in the past?
X squared plus y squared.
Well, we saw for where we have
X squared plus y squared equals r squared. Yeah.
We have x squared plus y squared equals r squared, but solve for y,
Okay.
and you'll get two answers. You'll get a positive and a negative answer. That's what I'm looking for. So the way we get around this is we draw the top half with a function, and then we draw the bottom half with a different function. So it requires two functions in order to draw this. Understand?
Yep.
Can we do it with a single function? Well, that's why we're here today. The solution is using what are called parametric equations or functions. So instead of having a function that goes from the real numbers into the real numbers, a single numerical input going to a single numerical output, instead what we're going to do is use the idea, I'm using capital F here, of taking a real number in. So I'm going to take in one number, but instead of spitting out a single number, I'm going to spit out an ordered pair. I have this here, okay? So instead of going from one-dimensional space into one-dimensional space, I'm going to go from one-dimensional space into two-dimensional space. Does that kind of make sense? And so the output, okay, let me read through this. That is, we take a real number in and send it to an ordered pair. The input is not necessarily the x-coordinate anymore. You know how in normal functions the x-coordinate is always the input? Here, our input is not necessarily our x-coordinate or the y-coordinate. In fact, the ordered pair that comes out, right, the two things that come out, because an ordered pair is a point, both of these coordinates depend on what we plug in. So what we're going to use to plug in instead of x is t. And we call t the parameter. So the function is going to take in a single number t and spit out a point, x and a y. Understand that? Get that idea? We're going to see it visualized here in a second. So both the x and y coordinates are functions of t. T is like a clock that's running in the background. So that's the way you want to visualize. Since you can't visualize the t on the graph itself, just think of like starting your watch and then starting to draw points. So at every point in time, there's a different point. Kind of makes sense? Should give you an example. This is a classic example here. Parametric equations of the unit circle. So what I'm going to do is I'm going to tell you what the x and the y coordinate are going to need to be to draw this circle. And both the x and the y coordinate, x and the y coordinate, are both functions of t. In the first case, x is some function f of t, and then the y is some other function g of t. And I've defined them to be cosine t and sine t. And then I've restricted my t to go from 0 to 2 pi. And let's take a look at what happens here. And I'll also explain to you where I got this idea from of using cosine t, sine t. If you just go to the unit circle, right, and you take a look at a point on this unit circle, it has an x and a y coordinate. And of course, we could use this equation as the relationship between x and y. This is how we would have got the two functions, top and bottom, but we don't want to do that. Instead, what we do is create this relationship that if I look at this angle as being t and create a right triangle, we know the hypotenuse of this triangle is 1, right? And therefore, if this side of the triangle is x and this side of the triangle is y, right, that's the distance x, that's the distance y, then cosine of t is what? Adjacent over hypotenuse, x over 1 is X. And then what is sine of t? Is y. And so what I've done is from that kind of breakdown of the unit circle, I've determined that I can just define my x coordinate to be cosine t and define my y coordinate to be sine t, and that should draw me the same thing. But notice that the x depends on t and the y depends on t. Yes?
This also means that we have to maintain no greater than 1. Yeah? Like if our radius goes beyond that.
Okay, so that's exactly what I was going to say next. So what would happen if I changed this 1 to an arbitrary radius like capital R?
Then we fail.
Well, what would change here?
It'd be x over
This would be x over capital R, and this would be y over capital R. So what would I want x to be? Solve that for x. R cosine t and R sine t would draw me a circle with radius R. Make sense? So this could be arbitrary. So really, there's a 1 in front of this and a 1 in front of this. But if this circle had a radius of 2, it would be a 2 cosine t, 2 sine t. If the radius was 1/2, it would be 1/2 cosine t, 1/2 sine t. Make sense?
Yeah.
Okay. So now, from this, what I've put here, this is, I don't want you to look at this as an ordered, like we call this an ordered triple. I don't want you to look at it this way, but this is the easiest way for me when I was typing up the code for this. Look at it this way. You have input, okay, like a t-table, and output, right? Man, all these markers suck. I know I might have to use these new ones. I don't want to break into that brand new pack. Let me just see how many of these are dead. Okay, so let's just try this. Remember, the output is a point. It's cosine t, sine t, and the input is t, right? So what would happen if I plug in 0 for t? Where would I be?
You get 1 with cosine.
I get 1, 0, right? And that's a point, 1, 0. And on my circle,
That's 0 pi or 2 pi.
that's where I'd be, right? This red dot? Make sense? So do you see this major difference? Instead of x, y, number, we have number point. Let's pick another value of t, but let's pick something that we know we can do cosine and sine of. So how about pi over 6? That's a common angle, isn't it? Pi over 6. Cosine of pi over 6 is root 3 over 2. Root 3 over 2. And then the y coordinate sine of pi over 6 is 1/2. And that's right here. You can see it here. So do y'all understand how this is working now? Input, and then this is actually like an ordered pair there. Understand? All right. So if you go back and you remember, try and remember here, what broke down when we were trying to define a circle as a function. Vertical line test failed, didn't it?
Yeah.
So notice here, let me move this a little bit. Man, this is just perfectly not the right size. Let me move this to pi over 4. If we go pi over 4, root 2 over 2, root 2 over 2, right? I'm recording, yes? Okay. Back in the previous circle, when we were trying to do this, can we look at this as a function, fail the vertical line test, because this point and the one down here corresponded to the same x value, right? The input x had to spit out 2 different y values. But to make this point happen now, all I need to do is move my angle. Yep, it's going to be, let me move it all the way around here. Right around there, right? So 7 pi over 4. So if I were to go down on this, 7 pi over 4 is going to spit out root 2 over 2, negative root 2 over 2. And so you see I'm getting these 2 points, I'm still getting them, but the input is different, right? The input's different. So there's no input that goes to 2 different outputs anymore. Yes?
Is that because our inputs are radians or because our output is an alternating wave
It has to do with the fact that our inputs are not part of our graph.
They're not a Cartesian point.
That's right. Well,
It's just a radian. It's just.
it's the radian part of it doesn't matter because I could just plug in 2 here, cosine of 2, sine of 2. What's making this work? Okay, what's making this still a function is the fact that no single input goes to 2 outputs. That's what's making it a function. And so what about this? This is kind of a good question. I don't think I made this work. You know what? I might have to just change the code real quick. Like I said, I did all this yesterday, and I knew I was going to have some issues here. Let me just do something real quick.
So it all depends on the angle, not on the actual x coordinate.
Okay, so this is a little different now. So let's go back to that pi over 4. There was pi over 4, right? So I got this point. That was this one right here. Now, watch what happens if I try and go around. I've got to make this smaller. There's just no way I can keep working like this. Okay, I'll move the point in a second. All right, so we're working with this point right here. What happens if I keep going with my angle? Yeah, and I keep coming, and I go back, and then I get back to this point. Have I failed to be a function?
No,
Why is that still not a problem?
because you said so.
Your input isn't the same as.
That's right, your input is not the same. Your input's what? 9 pi over 4. So down here on this chart, I'll just continue it over here. Your input's 9 pi over 4, and it's spitting out the same point at pi over 4, root 2 over 2, and root 2 over 2.
So you're allowed to have the same output.
That's right. You can go to the same point, you just can't go to 2 different points. That's what makes a function a function. Like, think about this function, classic function, f of x equals 3. We all know that's a constant function, right? Okay, and if I made a t-table for this, x, y, 0 would go to 3, 1 would go to 3, 2 would go to 3, any number would go to 3. It's okay if they all go to the same place. It's okay if 2 different inputs go to the same output. I just can't have one input go to 2 different outputs, right? And this is still qualifying. So by using this concept of parametric curves or parametric equations, I can actually draw things that used to be problematic for us, right? Things that would fail the vertical line test. Now we don't have a vertical line test. There's not a vertical line test for this. You just throw that out the window. Yes?
Is this a bit like the flowers that are in the book?
Yes. Uh-huh. Yep. Yep. We're getting to that. That's 9-3. There is no vertical or horizontal line test here. All right? So back in the day, like now that you've seen this, okay? We've kind of stepped outside of the fishbowl a little bit. If somebody asks you right now if a circle is a function,
Be like, yes, it is.
your answer should be it depends.
Yeah, it can't.
It's not a function of x.
No, it's not.
It's not your traditional y is a function of x. No, it's not. But if you look at it and you draw it parametrically with parametric equations, then it satisfies everything you need to be a function.
So the vernacular would be is it's a parametric function of t?
It depends on what your variable is.
Yeah, you could say that. I think you could say that without anyone arguing with you. Yeah. Okay, so let's take the original problem that we had here, the original traditional function that we had, which was I was using x squared as my example. And what we're going to do is we're going to look at that problem as the old problem, but from the new perspective. What we want to do is graph this still, right? We still want to graph that parabola, but we want to do it with parametric equations instead. All right? So what we need to figure out is how we map this t into an ordered pair. And it's written up there for you, so these notes are kind of spoiling it for you. But let's see if you can make sense out of why I chose what I did. I'm going to let the x coordinate be t and the y coordinate be t squared. Do y'all see that from the notes right here? X is going to be t, y, which is some other function of t, is t squared. Do y'all see that? Yeah. So what happens when I start making a t-table out of this? Let's plug in 0. What does it spit out? 0, 0, right? When I plug in 1, it spits out 1, 1. When I plug in 2, it spits out 2, 4. Isn't this just, you're almost cheating a little bit? You're just calling the x coordinate t. And then the y coordinate is just that function right there with x replaced with t. Right? Right? So that's a function. Well, it was a function already, but now I'm using parametric equations instead of traditional functions to draw the same exact thing.
But so all regular functions, to make it parametric, you just need to replace x with t.
Exactly, that's what I was going to say. So if you take give me any function here, let's just try something else here. If we wanted to do, let's say, the traditional function sine x, but we wanted to graph it parametrically instead, we would just let t be t, let the x be t, and then this would become sine t. Okay? So your input, your x coordinate is just the t, and then your y coordinate is just that function at t.
But
Make sense?
T could be anything.
So would it be
Yeah.
a function of t or is it a function of x?
But both of these are functions of t. This is a function of x. But this is our old way of looking at it. If you look at it from the new perspective, each of these is a function of t, right? T is the input. These are individual separate functions of t. Okay. Then we can take problems that used to cause us issues and turn them into functions, like the classic problem
Like functions of y.
x is equal to y squared. Now, we know from college algebra that's a parabola that opens sideways, but that would, in our traditional sense, fail to be a function of x because it would fail the vertical line test, right? So what we're going to do here is exactly opposite, opposite of what I just did, right? Instead of letting the x coordinate be the t, I'm going to let the y coordinate be the t. All right? And then the x coordinate will be whatever this function is,
So t squared.
t squared. Does that make sense? You're basically doing this. This is saying y is equal to t, right? That's what I'm saying. And then you go up to this, what's x? What's the x? X is y squared, but what's y? T. So this is t squared, right? Understand? And if we graph this and you do your inputs and your outputs points, you will get this. You will get this. And again, for each input, this input here and this input here, right? To get these 2 points that used to cause a vertical line test issues, the input for both of these points is different. It's a different input. Do I need to do a t-table for this, or y'all okay with it? You're okay?
He wants to see it, but
Who's he? Do you want to see a t-table? Why?
He said, wait.
You just want to see it? I'll do it. I mean, I don't mind. Let's just,
He's like, why?
let's verify it. Let's just verify. If this is t squared t, let's see how we could get these 2 points here. 2 points, one on top, one right below it. So what do these both have in common? Their x is the same, isn't it? But their y values are different. So let's just pick a y value here. It doesn't have to be what this graph is showing. How about we go like 2 here and negative 2 here, right? So we know that this point right here has a y coordinate of 2, right? And this one has a y coordinate of negative 2. So if I'm using this point, that means t would have to be what to get this one up here? 2. And what's it going to spit out? 4, 2. And then if we plug in negative 2, what do we get? 4 and negative 2, right? Understand that? Let's graph these 2 points. You go out 4, 1, 2, 3, 4, and you go up 1, 2. That's that point. The other one, you go out 4, 1, 2, 3, 4, and you go down 2, and you get this one. So you see, I'm picking up both of these points, but there's two different inputs that create those 2 points.
Can you do that with, so this is 2D, could you do that in 3D then?
Oh yeah, in Cal 3 we do parametric equations where you have x, y, and z.
Hooray.
And so you go three-dimensional with it.
And that would be, I guess, water.
So this is kind of groundbreaking for us because we now have ways of looking at curves that used to be problematic. Maybe I should back up. All the calculus we've ever done has relied on dealing with functions. The only calculus that we've ever tried where we didn't have true functions was when we had to use implicit differentiation. That was the only time, but that was it. Now, it looks like we're setting ourselves up to be able to draw curves that are still functions, so we should be able to do all the calculus that we did in the past with these. Derivatives, areas, arc lengths, all that stuff, which we'll do, all right? That's 9.2. It sounds terrible, but it actually turns out to be pretty nice. Okay, so I've shown you a couple of examples. The classic example of the circle. We took the x squared and we said, hey, we can even look at that as parametric. Then we did x equals y squared, a sideways parabola, said, hey, we can do that parametric. And now we can open ourselves up to just about anything.
Hooray.
So here is just one I came up with, or the book comes up with. The parametric equations are the x-coordinate is sine t minus sine 2.3t, and the y-coordinate is cosine t. T is on the interval 0 to 4 pi, and if I do the t-table for that and plot it, this is what I get.
It looks like my hair in the morning.
And
Looks like that last spaghetti.
so I'm going to start plugging in t, all right, starting at 0, I'm going to start plugging in t, and I'll slow it down a little bit.
It's like those awesome GIFs of the little atoms.
Okay, so what you have here, and this is why parametric curves are so important. This is starting to look a little bit more about like things that we would see moving around in nature, in real life, right? When things move around, they don't always have to, like, you know, if you take a, let's just take an ant, okay, crawling on the ground, and you say, okay, I'm going to let this ant go and start following its path, right? So the ant starts going like this, and you're like, oh, I'll be able to calculate its tangent, right? And then all of a sudden the ant turns and goes like that. You'll wait, you can't turn like that because I can't do calculus anymore because you're no longer a function, right? Like, you don't have control over things in the real world like that. You can't always force things to be functions of x. But what I'm telling you is that this is still a function now. Even though the vertical line test is no longer there, but that's more like, you know, real world. Does that kind of make sense what I'm saying? Okay.
I guess it's like the traveling salesman is one of those math problems that they're trying to observe nature. Right?
Yeah.
They have watch bees and stuff.
Yep. And then now imagine this in 3D. That's in Cal 3, that's what we do. So you have a single output time, but you have, instead of an ordered pair coming out, you have an ordered triple coming out. You have a three-dimensional point. And so you start moving that around, you get what's called a space curve. It's in 3D space. And now that really does model real-world stuff, right? So these are very, very powerful things, this idea of parametric curves. And then there's pretty much limitless possibilities here. Here's a classic example, a cycloid.
That creates a very specific
Bless you.
kind of thing. Whenever you're like rolling things down a hill, if you use like a straight ramp or like one that's like down fast and then like that, a cycloid will create the fastest way to get anywhere, like due to gravity. Like if you have the same mass, same shape and all that, you drop it, the shape of the cycloid makes it get there first every time.
Okay.
You should watch a video on it, it's really cool.
Okay. A cycloid is the curve that's traced out by a stationary point on a circle that's rotating. So imagine you're driving down the road and you get a rock in your tire, right? What's the path of that rock through space, right? This is what it would be. So let me back it up a little bit. And hopefully this doesn't go too fast. So the wheel's turning. There's the rock that's stuck. And you can see the path of the rock is there's some violent things happening to this rock, right? Because, this is nice, right? But what's happening here? That's an abrupt change in not only your speed, but your direction, right? You have a major acceleration here. And, right? That's what would happen with a rock stuck in a tire. This path right here, this path is called a cycloid. Now, how do we draw that cycloid? This particular one is 2 times the quantity t minus sine t, and then the y-coordinate is 2 times the quantity 1 minus cosine t. These are the parametric equations that you would need. There's 2 of them, right? One for x and one for y to draw this cycloid. Yes?
Did you look up that formula or did you just hammer
This one's out of the book. I'm following the examples in the book for this. Okay?
Do you know how to get that formula?
You can derive this, yes.
and prove it?
Yes. Yep.
Please don't.
He's like, I did it. You were a baby.
All right. Now, just as a recap, your general formula for parametric equations is this. Your x will be some function of t, your y will be some other function of t, and then your t is going to be usually restricted to some domain, but doesn't have to be. All right? You can have t just be all real numbers. In the event that we restrict it on a closed interval, we use alpha and beta instead of a and b. A, b is what we used for functions, right? When we were doing calculus, we said, hey, let's find the area between a and b. We're going to use alpha and beta so that we don't confuse it with a and b. All right? Because wasn't a and b the restriction on x? Here, alpha and beta are the restrictions on t. And t doesn't necessarily even appear on our graph. So we have to pay attention to that. And lastly, real good news, your graphing calculators can do parametric curves. So if you have your graphing calculator, you can take it out right now. If you don't worry about it. But
See, I found it. I'm curious about that. I would love, look, it changed everything.
remember this? Yeah, we talked about this. All right. So look, not everybody's calculator is going to be able to do this, but if you got a TI, you should be in business. Anyone not have a TI? That'll do it still. Okay. So what you want to do is go into your mode, and you want to look at where it gives you the option of like function. You should see something that says like para. Then you should see something that says like polar. And is there even one like sequence or something? Okay. Well, and yeah, so para, I want you to select para. Now, I'm assuming you all know how to graph things on your calculator. Like you've graphed things before, right? Maybe? Okay. So select para, and then now exit out of that and go like you would go to graph something now. And tell me what you see on your window when you go to try and graph something. Okay, you should see x1t, y1t, x2t, y2t, something like that?
Sort of. It says xt1, y2.
xt1, oh, xt1 or something?
That's what I've got.
Yeah, okay, that's this. Yeah. So here's how this works. Your calculator is saying, all right, you're going to give me the parametric equations. These come in pairs, okay? Those two, every group is one function. So when it says x1 of t, let's do this one. Let's try and do that one, y equals x squared. What was the parametric equations for this again? T went to what? T squared, right? Okay, I want you right here for x1 of t to put t in, and yes, you have to use t, you can't use x. So find your t variable button.
Actually, it'll automatically do it.
Not all of them do. So
I have a T button.
yeah, you just have a t button. Yep. Anyone not find t? Everyone's good? Now on the y of t, you need to put t squared. And then hit graph, and I bet you're going to get the right side of a parabola. Okay? So here's why it gave you the right side of the graph. By default, okay, the default setting in the calculator is that the restriction on t be between 0 and 2 pi. Because most of the time, when you're doing parametric curves, you're using trig functions. And so it defaults 0 to 2 pi. You need to change that if you wanted to draw the whole parabola. So what you do is you go to Window, And then it says something like T min, T max. Do y'all see that? And change those to like -10, +10. So like -10, 10. And then graph again. Did you get the whole
Do
thing?
we need to change the
Yes, I did.
T-step?
T-step, no, that has to do with how often it's calculating to get points. And sometimes when you're trying to get more accuracy, you make that step smaller. But in general, I've never really needed to adjust the step.
Okay.
Yeah.
Cool.
Okay, so now, next thing, let's try the other one, x equals y squared, which was the thing that our calculator used to not be able to graph, right? Like we could not graph a sideways parabola using the traditional graphing techniques of this, you know, the traditional function mode on our calculator. So what changes here? This is t squared and t, right? And then graph again, and you're going to have both parabolas, one opening up, one opening sideways.
Oh, wait. It says error. Oh, hold on. I see what I did. Yep, I see what I did.
Got it? Did it graph it sideways?
Yes, it
Okay.
did.
All right. Let's do one more.
This is really cool.
Let's do this. Let's do x is equal to sine y. Can you graph that for me?
Yeah, sure.
And you can either add it to these or you can take these out. I don't care. If you want these still up there, you can keep them up there. But
Sine y. Doesn't that mean that y?
I don't know what happened here.
so if I want to graph this,
That'd be T.
this is a traditional function of y, right? Not a function of x. So whenever we want to do functions of y, we always let the y be t and the x be the y, the function of
Sine t.
sine t, yes. Like that. So t is y, so that's a t, so x is sine of t. And you should get a sine curve opening up the
I
y-axis.
just have to zoom in.
Very like flat. I just got it.
You probably have to change your zoom for that to adjust. Yes?
Can you just graph inverse sine
Woo.
of a function?
Can you graph inverse sine?
Like to,
Mine turned into a wiggy
instead of going around this whole way, this way.
So would that be like?
Yes. Yeah, but there are domain restrictions on arcsine. So you're not going to get the whole graph, right?
I got what looked like a sine curve going up the y-axis.
Yeah, that's the way it's supposed to look. It should look like this.
Almost like a DNA helix.
It should look like this.
Yeah.
Yeah, because it's sine of
Yeah.
y.
So why isn't it like this?
Because
Why
you
isn't it the dotted
would
one?
need to do a negative sine t or whatever so that it
Yeah, remember the sine curve as the traditional sine curve when it starts at 0 and then it goes positive numbers, then negative, right? So when you're here going this way, right, when you go to the right, that's actually positive numbers, right? Positive x values. And then it goes negative x values, positive x values, negative x values.
Would there be much difference if we graphed the function that we did vertically and then did another function of negative sign or cosine? Wouldn't it be the same?
Wait, say what?
So you know how we just did a vertical sine t with positive?
Uh-huh.
If we did a negative sine t, we would complete what you were saying. Why isn't it?
Mm-hmm.
Yeah, you would flip.
Couldn't
the
you also
y
just do
axis.
cosine and have it do that as well, or would that not? It would run parallel to them.
Well, cosine would not do the same because it would have a little bit of a phase shift. It would start here
Right, so it
and go
would
like
actually-
that. So
yeah.
it'd be a little bit off, but.
Yeah. I realize that.
Okay, so now, back in the day when we were doing areas between curves, do you remember that? Do you remember when we were doing areas between curves?
Yeah.
And sometimes they were functions of y, not functions of x, but you still had to graph them. Like now you can actually have graphed them. Like you can go back. I know, Nathan, were you the only one, I think, that came in and got help, and I showed you how to do this back then just so you could verify with the graphs. Okay, that's it. 9.1 is done. That's just introduction to parametric curves. I have not come up with any homework assignment for this yet, okay? So I will let you know when that happens. What's this all about? I know I've been in chapter 9 before. I just haven't been here in a while. It's been a while.
So we're one of your best classes, right?
You're my best class ever.
So we should like not have to take the final.
Yeah.
Well, it's just like,
We shouldn't have.
I
to take
muted
the
it
final.
just then. I muted it just then.
It's the best.
Okay, moving on. Calculus with parametric curves. Everyone have a 9.2 in front of them there? Okay. The slope of the tangent line to a parametric curve. So we remember that in general, in Cal 1, that the slope of the tangent line was dy dx, right? dy dx is the slope of the tangent line. So I'd like to see if we can come up with a formula for dy dx. Now, we're going to use this very, very nice fact that dy dt can be rewritten, that's not dy dx, right? dy dt can be rewritten as dy dx times dx dt just using chain rule in Leibniz notation, because these dx's really would cancel and you really get dy dt, right? So this is just a clever way of writing dy dt, is as dy dx times dx dt, right? Then solve for dy dx. So just divide this out on this side, and what you get is this formula right here. dy dt, or sorry, dy dx. So the slope of the tangent line should be the derivative of y with respect to t divided by the derivative of x with respect to t. Now, what's y? If we're in parametric form, isn't y some function of t, like g of t? And isn't x some function of t, f of t? So all we're going to do at the end of the day is take the derivative of each of the independent parametric equations with respect to t, take the y1 and divide it by the x1. That's going to be the derivative, slope of tangent line. So let's go back to that unit circle. Let's find the slope of the tangent line on the unit circle. Now we need to remember what the parametric equations are, right? To draw the unit circle, the x-coordinate is cosine t, the y-coordinate is sine t, and t is going to go from 0 to 2 pi. That will draw my unit circle. First question, find the slope of tangent line at the point root 2 over 2, root 2 over 2. What is the equation of this tangent line? Where's the slope of tangent line horizontal? Where's the slope of tangent line vertical? This is the type of problem you would see on the test, on the final, all right? But let's work through it. All right, so let's start out. We have our parametric equations. X equals cosine t, y equals sine t. T is an element of the interval 0, 2 pi. Hey, if I made this right endpoint 2 pi, if I made that a parentheses instead of a bracket, would I still draw the whole circle?
No.
very,
No, you'd have to like.
Well, you just have a circle on zero.
Because you can't.
I start here, right? That's my first point. And I would go around all the way until I got to
like,
2 pi without getting to 2 pi. But would that draw me a closed circle?
yes, because 0 is still the same point.
That's right, because 0 is the same point. These are the exact same points, and you're including 0. If you put a parenthesis here, you would draw the whole circle closed. So this is kind of optional. It can be bracketed or it can be parentheses on the 2 pi. Just FYI. Okay? Now, I would like to know the slope of the tangent line at the point root 2 over 2, root 2 over 2. So first, let's find the formula for the slope of the tangent line. dy dt is going to be, I don't know why I said dy dt. I don't know why I wrote dy dy. I meant to write dy dx and say dy dx. Right? The slope of the tangent line. What is this? Okay. The slope of the tangent line should be the derivative of y with respect to t over the derivative of x with respect to t. So what is the derivative of y with respect to t? Well, that's that, right? Derivative of that, which is cosine t. Divided by the derivative of x with respect to t, which is just negative sine t. And that's just negative cotangent. I'm going to write one more step, just put the negative out front, like that. This is equal to negative cotangent of t, which is kind of weird that we have cot t, right? Cot t. Weird. So I'm going to put the t in parentheses so we understand what's going on there. All right. Good? All right. So part A said find the slope of the tangent line at the point root 2 over 2, root 2 over 2, right? But to find the slope of the line, what do I need? This is the slope of the tangent line, right? Yeah. What do I need in order to give you an answer?
Plus the point.
Do I need a point?
Yeah, T.
I need a t, don't I? I need to know what t is. So I actually need to figure out what t got plugged in that took me to the point root 2 over 2, root 2 over 2. Pi over 4. So there's a little subtle thing here you have to pay attention to. At the point root 2 over 2, root 2 over 2, right, t is equal to pi over 4. You have to be able to make that connection. See, you're not plugging in root 2 over 2. This right here is not getting plugged in any way into this. It's the t that generated that point which tells you where you're at on the circle. So now I take that information, so I know that dy dx, right, is going to be, I'm going to use this one right here, negative cosine of pi over 4 over sine of pi over 4. And what's cosine of pi over 4?
Root 2 over 2.
Root 2 over 2. So negative root 2 over 2 over root 2 over 2. So your answer should just be negative 1. Negative 1.
Is there a reason you chose sine and cosine instead of the cotangent?
Just easier to plug in pi over 4. I think it's easier because we're all experts when it comes to like the trig functions at the common values.
All right.
Yeah. Yeah. Okay. Good? Make sense?
Yep.
All right, so let's just verify this by going back and taking a look at the graph. If I go to that point, root 2 over 2, root 2 over 2, I should first of all have, oh man, okay, I'm going to have to just type in pi over 4 here.
This is cellophane.
Unsafe.
What does that mean?
Content.
It's a cell context.
There we go. All right, so there's pi over 4. And what I did here just for fun is I'm telling you what the input is. That is pi over 4. The output, this is root 2 over 2. This is root 2 over 2, and I actually had it compute the slope there. So that verifies. And don't you agree with just visually the slope should be negative 1? Yes? Okay. Now, the next question, part B, which you have in front of you, says to what? What is the equation of the tangent line? So this is the slope of the tangent line, right?
Isn't it just y equals negative x?
Close, but remember for part B, we have to use this formula. Y minus y1 equals m times x minus x1. All right, that's the old equation for a line if you know its slope and you know a point. So do we know the point x1, y1?
Yeah.
What is it?
Square root of 2 over 2.
That's root 2 over 2, root 2 over 2. Both the x and the y coordinate are the same, right? So the point we have, this is root 2 over 2, this is root 2 over 2. Do we know the slope of the tangent line there?
Yep, negative 1.
Negative 1. So this is just going to be y minus root 2 over 2 equals negative 1 times x minus root 2 over 2. And then that's the equation, isn't it?
Yeah.
You could solve that for y and everything, but that's That's the equation. Questions?
I think
I don't know, when it asked me, like, when I first saw it, I
Mhm.
thought, like, I would have written it out, trying to write it out as a parametric, like, equation instead of a,
The parametric equation.
like, the question is, what is the equation of the tangent line?
Mhm.
I thought parametric before, I thought that, would that be, like, completely, like, wrong?
No, that would be working a little bit harder than you have to, though. You could write this as a parametric equation, though. Okay, here's what you'd have to do. You'd have to solve it for y, like this, and then plus root 2 over 2, like this. And now, this could be written as parametric equations. You would let x be t, and you let your y be all of this with t plugged in for x. But again, that's...
We already had solved it for y, though, I guess, right?
Well, when I said find the equation of the tangent line, you can, when someone tells you find the equation of the tangent line, it doesn't matter what that equation, what form it's in, right? I mean, it doesn't say specifically to use like the standard form. You could use parametric form, it wouldn't be wrong, but I don't think it's necessary. Like this is okay. Yeah. What does part C say? Where is the slope of tangent line horizontal? What does that mean? Yeah, part C is saying when is dy dx equal to 0, right? And so dy dx we already knew was negative cosine over t over sine t, right? We want to know when that's 0?
So whenever cosine of t equals 0, so that's going to be pi over 2 and negative, or
Yeah, a fraction can only be 0 if the top's 0, right? A fraction can only be 0 if the top is 0. And so we want to know when cosine of t is 0.
pi over 2.
And this is just, just go back and imagine you have a unit circle. Where is cosine 0? Cosine is 0 here and here, right? At pi over 2 and 3 pi over 2. That's if we're looking only between 0 and 2 pi, right? Yeah, otherwise you have a general solution. So at pi over 2 and 3 pi over 2. Yes? Where are those points on our circle?
right there.
So imagine pi over 2 is up here, right? Now we could verify, how could we verify that these 2 points are the kind of like north and south poles of this circle? We'd have to plug pi over 2 into the original parametric function, right? And you would get this point. And if you plug in 3 pi over 2, you get the point on the bottom. And it's obvious to you, yes, that the slope of tangent line up there is 0?
Yeah,
Yeah, and then down on the bottom is 0 also.
and then the horizontal.
Okay, so now the next question, part D, is when is the tangent line vertical?
0, pi, 2 pi.
So where are you getting that from?
Well, 0 is because it's right there, then pi is on that side, and then 2 pi.
So visually you're getting it?
Yeah.
Yeah, but you need to get it mechanically.
Mechanically.
Okay.
Because this is like an example where it's easy to see it, right?
Then whenever sine equals 0.
So we're going to have vertical tangent lines when the derivative, remember, this is derivative is 0, derivative is positive, derivative is negative. Vertical lines have undefined slopes, don't they? And so what you want to know is when is, this is part D, when is dy dx undefined? So you take your negative cosine x over sine x, and you ask yourself, what would make this thing undefined?
Sine.
If sine is 0, right? Sorry, I put x's, sorry. Okay, so this is going to be undefined if sine of t is 0, and then you just solve that, and you get what? T is 0 and pi and 2 pi. Because I included 2 pi in my interval. And we can verify that. If you were to come here, the tangent line would be vertical. Here, tangent line would be vertical. That's it. This make sense? Okay. Good. Let's move on to areas. Now you have all this in front of you, so I'm just going to leave this like as a small font. Okay, remember that when we were doing integrals, areas under curves, we had some function of x. Y is equal to some function of x. We cut this thing off between a and b, and we were trying to find this area. And it turned out to be the integral a to b of f of x dx, right? That's our integral. Now remember, f of x is really just what? Y, right? Yeah. That's just y. And dx, here's how I'm going to figure out what dx is. If I switch to parametric, my x is some function of t, my y is some function of t, and my t is in some interval alpha beta, right? If I take the derivative of x with respect to t, that's just f prime of t, right? So it's like the derivative of the left side with respect to t is dx dt. The derivative of the right side with respect to t is f prime of t. Yeah? And then solve for dx. So just multiply both sides of this by dt, and you get that dx is equal to f prime of t dt. And then rewrite this integral. What we're going to do is switch f of x to y, but what's y? No, what's y?
Sorry, G of t.
Y is g of t. Okay, so now we get g of t here. And then what's dx? F prime of t dt. So that comes right here. So this piece right here is what y used to be, and this piece right here is what dx used to be. And now my integral is with respect to what variable? T. So my limits of integration change from a to b to alpha beta. Does that kind of make sense? Isn't that pretty awesome? I mean, we can find the areas of these parametric curves. So we're going to start pretty bold here. We're going to try and verify the formula for the area of a general circle of radius capital R. Now we all know the area of a circle of radius capital R is pi r squared, right? We were going to prove it. Now, do y'all remember we proved this before?
Yeah.
I proved to you that the area of a circle is pi r squared. We did that using trig sub, or maybe a formula in the formula sheets. I split it into 4 sections, right? And multiplied it. We're going to do the exact same thing. We're going to try and find the area of a general circle, but we're going to do it by drawing it parametrically. We're going to draw the circle parametrically. All right? So I've defined my parametric equations. X is equal to capital R cosine t, and then y is equal to capital R sine t. And notice also I'm restricting my t between 0 and pi. So when I draw this, right, when I actually draw this curve, it's only going to draw what?
Half.
The top half, right? Let's find the area of this right there. And then we'll double the answer. Agreed? Now, why am I using capital R in front of this?
Because it's
We talked about that earlier, right? The capital R is what's going to adjust your radius. Okay, the formula I need is integral from alpha to beta of g of t times f prime of t dt. For us, this becomes integral from 0 to pi. What's g of t? R sine t, so r times sine t, times what's the derivative of f with respect to t? Negative r sine t, then dt. Yes? Now, we can pull out a negative r squared, can't we? Because capital R is